Hello everyone, and welcome back to Electronics Prepper, the channel where we try to learn as much as possible about electronics to become more self-reliant with technology and prepare for the future. In the last video, I have shown you that I was working on a special kind of multimeter that is useful, will be useful in order to measure the efficiency of DC-DC converters. And I've explained several reasons why we might want to build such a multimeter, since it's not all that difficult and it makes our life very easy, especially if we want to perform these measurements repeatedly, especially if we want to work with more than just 2 or 3 DC-DC converters. Now, it took me a little bit longer than I would have wanted to come with this video, which is the second one in this series. There are going to be 3 in total. It took me a bit longer than I would have wanted, simply because I made some mistakes designing the circuit that I will show you today, and in the end he just didn't work good enough. The errors that I was experiencing were a bit too much, even for me. And I'm not a very pretentious person, but even for me, the errors were just not acceptable. So I had to just admit that I've had a shitty design and that I just need to scratch everything and restart everything from zero, at least with this circuit that I will show you in a moment, that actually helps the Arduino board to perform the correct measurements of the voltages involved here. So I redesigned the circuit. You actually have the circuit on the screen on the left side of the image, because on the right side you see an Arduino and a Nokia 5110 LCD screen. And yeah, now the circuit works pretty well. It uses some specialized op-amps, some specialized integrated circuits instead of just generic op-amps. So yeah, I'm proud enough to be able to show you this circuit today and to discuss what he does, why he is needed, and further advance our work into getting our multimeter finished. Before we dive deeper into the smaller details about what I've done here, why, how everything works, please allow me to thank the sponsor of this video, which is PCBWay. And at the same time give you very good news. They are currently organizing their 6th project design contest, and you can participate too. They have 2 teams this year. You can choose between participating with an electronic project, meaning a circuit board or a full electronic device, or just a mechanical project such as, I don't know, a 3D printed plastic object, or CNC machined object, or just a general product design. You can apply and upload the necessary files until 15 January. Let me show you. And if you happen to be the winner, you will find this on 8th March, of course, 2024. You can find all the details and the rules on the contest webpage. And in order to help you in the build process of your dream project, PCBWay can assist you with their PCB manufacturing services, PCB and components assembly, semi-D stencils, as well as 3D printing, CNC machining, injection molding, everything you need to get your dream project finished and apply for this nice contest and perhaps even win something. Both the link to PCBWay.com and to their contest are in the description. Now, thank you very much, PCBWay, for sponsoring this video, and let's get back to the circuit that I'm trying to show you. So, quick recapitulation from last video, in order to measure the efficiency of a DC-DC converter, we first, besides the converter himself, we need to have a power source of some kind, a power supply, typically a lab power supply. We also need to apply some form of load at the output of the converter, preferably an artificial load, an adjustable electronic load. And based on what voltages we have on the input and what voltage we set our DC-DC converter to have on the output, based on the input currents and output currents, we can basically calculate mathematically this efficiency. We, of course, need to take 4 measurements, 2 voltages and 2 currents, and this process can have some disadvantages, can potentially introduce some problems, and even if there's nothing wrong, it's still a bit inconvenient to have 4 different multimeters on a workbench, 8 different cables going everywhere, just to be able to, you know, measure the efficiency of our converter. This is what led me to want to design this multimeter and build him. Again, just for a really quick reminder, my efficiency multimeter is designed to work up to 24 volts, both input and output voltage, and 10 amps maximum current. This means that we cannot apply more than 24 volts on the input of the DC-DC converter, and also if we are dealing with a step-up DC-DC converter, we cannot have him output more than 24 volts on the output. Also, this whole multimeter works based on the idea that we have a common ground for absolutely everything. A common ground for the DC-DC converter, for the power source, external power source, for the artificial load, and of course the same ground for the multimeter himself. This means that we can measure step-up or step-down converters. However, we cannot measure the efficiency of inverting DC-DC converters, because those basically output a negative voltage with respect to ground, and also we cannot measure the efficiency of isolated power supplies. Though for those we will design a different multimeter, a different device in the future. Anyhow, in the last video I have shown you the power source, because I want to power this entire multimeter from a 3.7 volt lithium accumulator that I've recovered from one of my old cell phones. But of course an Arduino needs 5 volts in order to work, and not just the Arduino but the other circuits that I'm going to show you in this video. They require 5 volts to be powered. They cannot work with directly the accumulator's voltage, which can vary anywhere between 3 and 4.2 volts depending on the state of charge. So we need to take this low voltage and increase that to 5 volts, and that's what I've shown you in the previous video. I have created a rudimentary but good enough custom-made step-up DC-DC converter just for this purpose. In this video I will show you how do we do to take these measurements, these 2 voltages and these 2 currents, and feed them into the Arduino, so that later in software we can perform calculations, because the Arduino can only has an analogic digital converter that only accepts a maximum 5 volts. Okay, so we need to do basically 2 things. We need to, for the currents, we need to transform these currents into voltages, and we need to make sure that all voltage readings, including input voltage and output voltage readings, stay within 5 volts at all times. Even if we go up to 24 volts, we need to make sure that Arduino sees only 5 volts. So we need to basically attenuate these voltages a bit and perform some extra protection, preferably. So this is what I have here, and this is what I'm going to explain to you briefly. The circuit is simple, it's easy. It looks a bit big, but it's not. First of all, So we could call this, in English, we could call this signal conditioning circuit. I have noticed that in English you use this term to designate a circuit that takes a certain signal of a certain kind on the input and change that signal to satisfy certain conditions and output that signal towards another circuit. So this entire process is called signal conditioning in English. I'm mentioning this because, you know, maybe you, like me, are not a native English speaker, so you might not know all of these terminologies. Anyhow, this circuit is actually a double circuit. If you take a look on the upper side, upper half side, you will see that it's identical to the lower half side. This is because well, we need to measure 2 voltages and 2 currents, so the principle of measuring a current is the same for both currents. The things that we need to do for the voltages are the same for both voltages, so this is why we, technically speaking, have 2 almost identical circuits that are just built together on a single board with a few extra connections between them, and yeah, that's pretty much it. So I will explain half of the circuit, and the other half is identical. Okay, the first half deals with the input side, so the input voltage that comes from the power source into the DC-DC converter, and the input current again that comes from the power source into the DC-DC converter. So when I say input side, I'm referring from the perspective of the DC-DC converter. From his perspective, it's the input side. Okay, so probably the most difficult thing to do is the measurement of current. This is where I kind of fucked up last time, and I needed to just redesign my circuit and use a different solution, basically, because yeah, what I created before was not, which was just not good. So the easiest way and the best way for this particular project, because we don't need to complicate ourselves unnecessarily, is to use a shunt resistor here, where this ampere meter is. We want to put a shunt resistor. The higher the current that passes through him, the bigger the voltage drop across him. And we want to take that voltage and basically amplify her, because ideally we would have a very small voltage. So we want to take that voltage, amplify that voltage, and then send that voltage as a signal further to the Arduino board. And this is what we're doing here. I have chosen a dedicated chip, INA 180 A3 submodel. So to briefly show you this chip from Texas Instruments, it's actually a family of chips, of integrated circuits, that does low and high side voltage output current sense amplifiers. Basically, exactly like I've said, it is able to, I mean, the chip is able to measure the voltage that can be either low side, meaning relative to the ground, or high side, relative to the positive input. The voltage that passes through, that forms across a resistor, and amplify this voltage. And this chip is pretty good, has pretty good accuracy. So it's a good choice. Instead of just taking a generic op-amp and try to, you know, have 4 matched resistors in order to accomplish this, I've discovered that it's just better to use this kind of op-amp. This kind of, well, it's apparently it's called a measurement amp by some people, but anyway, let's just say current sense amplifiers. Now, there are all sorts of models that start with INA in front and have all sorts of other numbers after. 181, 199, 240, and so on. Like there are many models that do more or less the same thing. made by Texas Instruments. I have chosen this one, 180, because it's relatively cheap. It's something like 25 cents per integrated, something like that. It's well within $1 a piece, so at least if we buy I don't know, 25 at once or so, it's cheap enough that we can afford him, and it's also not a problem to obtain him, unlike other circuits, either chips that are still affected by this weird semiconductor crisis. This ENA 180 and other similar models can be easily found on the market. Now, this kind of chip comes in several variants. I have chosen A3 devices, and as the datasheet says, we have a different gain, a different amplification factor, basically. So for A3 devices, I have 100, a factor of 100, okay? They say volts per volt, but basically it's a factor of 100, because if you divide a measurement unit to the same measurement unit, you end up with essentially a scalar number, a number that doesn't have a unit of measurement. So anyway, this chip is pretty nice. He needs to be powered by from 5 volts. They say 5.5 volts maximum recommended, but the chip himself allows us to measure currents that flow in a circuit with a voltage up to 26 volts. Okay, so a lot higher than the power supply voltage, which is great because we have 5 volts for the Arduino anyway. This chip consumes quite a low amount of current, 260 microamps, so less than a milliamp. It can measure up to 26 volts current through a circuit up to 26 volts. We only want 24 volts maximum, so it's perfect. It's exactly what we need. And also, it's one of the simplest integrated circuits to be used. Besides him, you only need the shunt resistor, and optionally, you might need some extra components to protect against overvoltage on the input in case there are voltage spikes on the power supply rail. Okay, on the, well, not on his power supply rail, but on the input rail. Okay, and this is what we see here. I have a shunt resistor of 5 milliohms, and yes, you can actually find on the market resistors of 5 milliohms value, even though it's a very small value, but we can definitely find such. From either side of this shunt resistor, we have 10 ohms resistors in series with what needs to be 24 volts Zener diodes. Now, I didn't have 24 volts Zener diodes, so I chose to place 2 in series, each 12 volts, so together they make 24 volts. This makes it so that if we have voltage spikes of more than 24 volts on this line relative to the ground, the Zener diodes will start to conduct, and they will clamp the voltage on the inputs of this measurement amp, so they will protect him. Like I said, this measurement amp basically measures the voltage across the shunt resistor and amplifies that voltage with a factor of 100 in my case. If you were to choose a different model, like A1, A2, A4, then you would have a different amplification factor. For me, the amplification of 100 was good, because at 1 amp I have 5 millivolts across the shunt resistor. Multiplied by 100, that's half a volt. So I have half a volt per amp, and therefore I'm having 5 volts, the maximum voltage in this whole circuit, when I have 10 amps. So with this circuit, I can basically reach 10 amps. I can measure 10 amps of current. The chip has rail-to-rail output, which means that his output can go down to 0 and up to, I mean, very close to 0 and very close to the his power supply rail. So this makes it possible to have, again, 10 amps through the circuit that produces 50 millivolts maximum voltage on the shunt resistor, multiplied by 100 gives us maximum of 5 volts. This way we use the entire dynamic range of the Arduino's analogic digital inputs. Okay, now because the Arduino, let me show you, because the Arduino has 8 different analogic digital inputs. It's true that 2 of them are in common with E2C, how do you call it, protocol wires, but we don't care that much because we are not using an E2C device such as an LCD screen. Our LCD screen actually uses 5 different GPIO pins. We can definitely use all 8 ADC inputs, and we can basically improve the accuracy or at least the resolution of our readings if instead of feeding just four signals into our Arduino, we feed 8 of them. Basically we can take each signal, okay, because again we need to measure 4 things, so for each thing we will normally have 1 signal. However, we can apply some amplification to each signal and feed that amplified signal as a separate signal on another ADC input, and this way we basically have the possibility to have a slightly higher resolution for values between 0 and some of the values of our original signal. So let me explain to you a little bit better what I mean here. So this measurement amplifier, like I said, gives us 5 volts at 10 amps of current. However, let's say that most of the time we will be working with between 0 and 2 amps. Okay, maybe we won't go so often above 2 amps. It makes sense that we have extra accuracy for all the readings between 0 and 2 amps. This signal from our measurement amp, first of all, it's nice to send him to an RC low-pass filter to filter out potential spikes that might, I don't know, happen due to all sorts of reasons, because after all, we, at least in this project, we care more about the average value of our currents rather than you know, a very accurate measurement taken at a high sampler rate. So we have this R19 and C2 capacitor, 47 kilo with 47 nano. This constitutes 1 output, so I'm sending this to ADC 0. However, I'm also feeding this signal into an op-amp, a non-inverting op-amp, with an amplification factor of almost 5. This means that when the signal is between 0 and 1 volts, which is corresponding to a current between 0 and 2 amps, I will have on the output of this op-amp a signal that goes between 0 and 5 volts. So I can use another ADC input for every measurement between 0 and 2 amps, and that's gonna give me a bit more resolution, a bit more precision, okay? And in software, I'm basically switching between these 2 inputs. If the value on this input is low enough, I'm going to take her into account. If the value here reaches 5 volts, gets close to 5 volts, then I'm simply assuming that the input signal was just too big, so I'm going to read ADC 0, and I'm going to calculate everything based on ADC 0. And this is how we measure one current. The other current, like I said, is measured identically. I have exactly the same circuit, so it doesn't make sense for me to you know, explain that. And for the voltages, well, we don't need to do much, but I've chosen to put some buffers just to create an extra protection for the ADC inputs. Okay, so again, since I have enough ADC inputs, I can do the same trick with that I've done here, to basically have a higher resolution between certain values. But the thing is, I'm forced to do things in reverse, essentially. So if here we needed to amplify what was a relatively small signal on the input in order to get better resolution, here I need to do the exact opposite, because I have an input signal that can go up to 24 volts. So I need to, by default, I need to basically attenuate that signal. Okay, and this is why we have this voltage divider, root 30 47 kilo with root 33 12 kilo. Okay, this basically has an attenuation factor of almost almost 5. So we've got 59 kilo ohms in total divided by 12, about 4.92 attenuation factor. So this means that basically a 24 volts divided by 4.92 will give me about 4.80 something volts. And this is going to be my main signal for reading the voltage on the input. Okay. However, when the voltage on the input is between 0 and 5 volts, technically speaking, I could just take that voltage and read that voltage directly, and you know, in this process, basically I would get 5 millivolts of steps of resolution. So in order to do that, I have a second buffer that just takes the input signal through a resistor, a current limiting resistor, and just feeds this on the output as is. The reason why I've put these buffers is that no matter what happens with the voltage on the input, because these buffers are powered by 5 volts, just like the Arduino, the output will never go above 5 volts or below 0 volts. So these buffers basically give me a bit of extra protection. Also, I have decided to place one rectifier diode for each input that's connected to the positive you know, supply voltage of 5 volts, so that whatever voltage we have on the input, it will be clamped basically to 5.5-ish volts or so, so that even the buffers are relatively well protected. The input buffers are relatively well protected, and that's pretty much it. So basically in software, I do the switching in reverse here for the voltages. If when I was measuring currents, I was basically taking a look at ADC1 first, and if the value was good enough, then I was calculating the final value. If the value was too high, then I was switching to ADC0. Here I'm doing the opposite. I am reading ADC4, which can go from 0 to 5 volts. If the voltage that I read is within 0 and let's say 4.9, then I take that voltage as she is, and I consider that that voltage is what we have on the input. If the voltage is above 4.9 volts, then I'm going to assume that the input voltage was potentially higher than 5 volts, so I'm gonna switch to ADC5 input, and of course I'm gonna perform some calculations, because I know that, you know, the input signal was attenuated. So based on what I read here on ADC5, I multiply with this factor, and this is how I get my voltage. Okay, and this is pretty much the entire circuit. It's a lot simpler than the one that I was going to show you, but in the end I didn't, because it, like I said, he just didn't work properly. It doesn't take much to build this circuit, so yeah, it's pretty nice, pretty good. One more thing that I need to mention is that basically the inputs are kind of switched. So if we take a look at this diagram, okay, basically we have one circuit that is found here in place of these two measurement devices, and another circuit that needs to be placed here. So you know, the thing that I've labeled power input here, this comes from the power source. Okay, it's the output of the power source, and this will eventually go to the DC-DC converter. And on the other side, converter in, okay, this is this pin from the input of the DC-DC converter. Again, the ground is common for absolutely all circuits, so no need to even mention that. The output of the converter goes here into the second circuit in conv out, what I've labeled conv out here. It's the output of the DC-DC converter, okay? And the artificial load would be connected here at load out, okay? And of course, we want to measure the voltage on the input of the converter and also on the output of the converter. This is why I've taken this this wire here from this point for the first voltage measurement. And the second voltage measurement has its connection here on conv out, converter out. Okay, so that's pretty much it. This is how we measure two voltages and two currents at the same time. This is how we use some enhancements. We basically exploit the fact that, like I said, an Arduino Nano, at least an Arduino Nano, it needs to be an Arduino Nano, not an Arduino Uno or some others that do not have 8 ADC inputs. But Arduino Nano has 8 ADC inputs, so we can easily create this trick to, you know, have a little bit better measurements for lower values. And that's about it. And in terms of what we need to do on the electronics level, this is pretty much it. I will explain to you the software and what I've done in on the digital side. It's not much. I mean, the Arduino gets connected to a Nokia 5110 screen through 5 resistors of 10 kilo ohms each. But anyway, we'll discuss about this in the next video. If we do this, this is everything that we need in order to, you know, have all the voltages to feed the Arduino, and later just write the source code that reads these values, performs some calculations, and outputs values on the screen. And let me show you quickly before I finish this video. This is how the screen looks like. Now, these readings are not 100% correct. I was just testing here, you know, what I've created earlier, the circuit and everything. The software needed a little bit of extra corrections to account for some resistor mismatches, which is very easy to do. But this is pretty much how everything will look like. We will have a first line that shows the input, voltage and current, a second line that shows output, voltage and current, a third line that tries to measure, it's not a good enough measurement, but it's a rough approximation of the ripple voltage on both on the input and on the output, although we don't care that much about the ripple voltage on the input. The ripple voltage on the output will matter a lot more. And this is going to be something that you should care about, you know, because there are very, very cheap and very bad DC-DC converters that have just too big ripple, half a volt, sometimes even more than half a volt. Anyway, and finally, with a bigger font, we see the percentage, which is the efficiency of whatever it is that we are measuring. And of course, this is what we wanted. A nice automated calculation so that we don't need to bother with this. Anyway, this is pretty much it. thank you very much for watching this video. I hope you found him useful. I hope you enjoy what I'm showing you here and helping you, have better tools and devices in your mini lab. If you enjoyed it, please consider liking, hitting the like button, and perhaps even subscribing to the channel if you would like to see more in the future. Soon I will come with the third and last video for this particular project. I need to design a plastic case, 3D print her, and assemble everything, into an actual device, because I still have the circuit boards just lying around, not really connected to each other. So in the third video I will show you how I finished this project. I will explain the software, what I wrote in there, what I used. The software is not difficult. And in the end you will find on my Patreon page an archive with all the files, including the software needed to build this project. Thank you very much for watching this video. Also, thank you for those who are sponsoring my efforts. I really appreciate it. And I will see you soon in the next video. Bye bye.